Hi everyone, I'm back and I'm going to be talking today about the Algorithm Design Manual. Hi everyone, I'm back and I'm going to talk about the Algorithm Design Manual Chapter 1. I know I did 10 before because that's like my favorite chapter because it's very thorough. We're going to start back at 1, and Chapter 1 starts with an intro to algorithm designs. So what is an algorithm? An algorithm is basically a procedure to accomplish a specific task, and it's kind of the idea behind any reasonable computer program. So it's like the basis of what we do or plan to do for everything. And what I want to, on this first page, basically, and I wish I'd had this book when I was first learning, but it talks about what is an algorithm, and then it says what is an instance of that algorithm. So the first algorithm on the page is a sorting algorithm, and an instance is when you sort a particular type of data set, basically, a particular type of information. And so you don't have to reinvent the wheel. A lot of times it's an instance of an existing algorithm out there, and you just have to implement an instance of your data and information or technology on that algorithm. Um, Once we zoom through that, he talks a lot about algorithm correctness, which I think is interesting and I think is still a big problem, especially for us. Well, actually, anyone, because I've been to university and they didn't teach me this. But algorithm correctness. So there are likely many ways for you to solve a problem. That doesn't mean it is the best answer. And so he gives the example of going through and trying to find the quickest way to get through a certain subset of points, or the robotic tour optimization is what the chapter is. And he talks about the nearest neighbor. Well, going to the one right next to you is faster, but that's not always the case. And then he gives the example of the closest pair. And finally, we come around to it being a traveling salesperson algorithm, which is actually the best answer for that. And I feel like oftentimes when you're getting started, you kind of just throw random machine learning algorithms at a problem and you're just like, yay, I did it. But that's not the best way to have done it. And it's not really efficient for your client, which in this case would be your boss or that the boss's client they're doing the work for. It's not the best option for them, and it doesn't really solve the problem in the most efficient manner in the best way. And I feel like we get excited because we're like, oh, I can do a neural network. Great for you. You probably should have done a random forest. And so it's just understanding the context of the problem and applying the right algorithm to it. Um, and then section 1.3 is where I'm at. And I'm going through it as a summary. I'm not really going to teach it. But reasoning about correctness. So there's always a clear, precise statement of what you're trying to prove or what you're trying to do. If you don't know that, then you didn't ask enough questions. And I think that's where we get started in a lot of different ways. And I'm guilty of this all the time. I did it a couple of weeks ago where I didn't, like, I was excited because I was like, oh, I get to play with this tool. And I really shouldn't have. And so I jumped the horse. And I shouldn't have jumped the horse. I should have went back and made sure there's a clear statement of what they were looking for. The second is there's an assumption of things which are taken to be true and hence used as a part of the proof. So we assume certain things are true about what's going on. Like we assume if you're dealing with medical data, you might assume some sort of baseline or whatever. You're always assuming something. And third is there's a chain of reasoning which takes you from the assumptions to the statement you're trying to prove. And this is actually where he starts getting into actually, no, it's not. Jumping ahead of myself. But basically, we're always assuming things when we're coding. It doesn't matter what you're assuming. And you're trying to use those assumptions to do something. Especially if I always try to get people to understand there's different industries to like specialize in. And I typically specialize in research related fields. Not that I have a PhD or anything. It's just that I like those types of problems. A lot of more people will focus in where you can just use a tool and you can do it. Where if you're going into actually developing things and thinking about them, you can't just do that. You have to have some sort of reasoning and understanding behind what you're trying to do. You always have a set of allowed instances that you can do, like what does the data have, and then required properties of the algorithm's output, like what are the requirements for you to have when you're done. And you don't always have those inputs that you need to get that output, and so always making note of that is important. Okay, so this is the part I wanted to get to. One is asking an ill-defined question. I do this all the time. I'm getting better at it. Again, jumping the gun, but that's not the part. Okay, so the part I wanted to get to is the part about induction and recursion, which is basically the method of understanding and demonstrating incorrectness. And I'm just going to be honest, it still makes no sense. But it is a fundamental part of computer science. And it's basically you make a general condition and you break down the problem into a smaller piece, and the initial condition terminates the recursion. So you basically assume that what you're starting out with is true, and then you use that assumption to break things down and for it to prove itself, which you're just like, okay. But a lot of algorithms, especially when I'm going into like I don't know if you guys have ever done free code camp. You're doing those JavaScript things, or you've gone on like, I think it's Coder Bytes. You've done those Python things. A lot of those are recursive things, and no, you don't have to understand recursion in depth to actually do recursion. It's just interesting to think about. And I can't explain to you recursion again. It makes no sense to me, but it is useful assumption to work with. And that's pretty much all I wanted to cover in chapter 1. I don't think you need to know all of this. I think it's interesting information, but you don't need to know all of it. I do like this quote. It says, "Learning to think think recursively is learning to look for big things that are made from smaller things of the exact same type as that big thing. Basically, use all the smaller pieces to build up and prove the bigger thing, which is recursion, which is really cool when you're thinking about how to solve a problem." So I actually wanted to get to the first part of chapter 2, which is big O notation. And I spent lots of years never even hearing of this, already coding all the time. I was working in a bioinformatics research lab. I spent 2 of those years in college in a computer science program. They never taught it to me. So this is important, and it gives the background. So starting with a RAM model of computation, like random access machine, RAM. I didn't know that for years until this book. Anyway. So loops and subroutines are not simple operations, and basically to model how much time it takes, like back then it would take me 2 or 3 days to run one of my algorithms. And at the time I had no clue why it would take 2 or 3 days on a machine, and it's simply because it was an optimized algorithm. And so this tells you, like, big O notation is simply there to tell you best, worst, and average case complexity and find a way to compute that, which is important because, again, you don't want your servers running for 2 to 3 days on something that really should have only taken you an hour. And I feel also these days, because there's a lot of tools and packages compared to then, like, that was like Python 2, like early Python, Python a decade ago. Dang, I'm old. I'm not that old, but anyway, sorry, ramblings. But it was Python a decade ago, and so there's been tons of improvements. But and with all the packages, I feel like it's harder to do this. Like if you're in data science, you're using pandas or whatever, and it'll just basically cut you off and stop your notebook, and you're just not going to realize that your notebook stopped. But not so much back then. My computer should run all day, and I wasn't coding in a workbook either. But here nor there. But big notation is basically the upper bounds and the lower bounds of the time complexity of what's going on in the algorithm. And upper and lower bounds, you learn that in Algebra 1, like it stops here, it stops there. You never get away from math. But it's interesting to look at and to find that, and this will simplify basically knowing how efficient your algorithms are and help you make better ones. Um, Specifically, if you're having to code anything from scratch or you're trying to develop something, I always want to be sure that I'm talking about like research-based data science. Now, if you're in a company and they're working on general business tools, sadly, you're not going to do a lot of research-based algorithms. You're going to do more already done, and you don't need to reinvent the wheel. You just need to apply those tools to that set. I think that's where a lot of us become unsatisfied with work, is that it's just very repetitive. You're not working on anything interesting, and it can get a bit frustrating. So anyway, that is the first part of chapter 2. I haven't finished rereading the rest of chapter 2, but I'll do that and I'll talk about it probably next week. And I also want to reread Elements of Statistical Learning. That, or I'll learn, what is it, Databricks? I'm not so sure. I might go back to trying to invent myself a job. Um, don't know what that would be, though. I kind of like what I do. Anyway, if y'all have questions or want to chat with me about this, just comment below this video, and we can talk, have some data science fun. Anyway, y'all have a good evening.